We are, as promised, is we're going to be looking at moles and gases. All right, so there are two things left for us to do: moles and gases, and moles and equations. All right, now I'm leaving moles and equations for last, because moles and equations, what I like about it is that it ties in every aspect of moles. We looked at moles and solutions with your titration, right? That is what it's actually called in your textbook, moles and solutions. All right, so technically, it's known as volumetric analysis, because you are trying to figure out concentration and volume, right? And so you use moles and mole ratio and those things. Your moles and equation ties in looking at number of particles, looking at mass, looking at the molar mass, and what we're about to do now, which is looking at the gas. Because when you think about the reactions in chemistry, many of them produce a gas, and we learned about two such reactions when we were looking at acid and bases. An acid reacts with a metal, and that produces hydrogen gas. An acid reacts with a carbonate, and it produces carbon dioxide, right? And what we can determine now is just how much of what volume of the gas is being produced, and what volume of hydrogen can be produced when we do such a reaction, what volume of carbon dioxide can be produced. So those are the things that we're going to be calculating. All right, now it says that gases have very small masses, and we know that from way back in the day when we're looking at atomic structures and the characteristics of solid, liquid, and gases. So they have very low densities. And so what the chemists have done was to find a relationship between the number of moles of a gas and the volume that the gas occupied. When we look at Avogadro noticed that all gases, it's very important to know this, all gases under the same conditions of temperature and pressure and occupying the same volume contained the same number of molecules. All gases, ladies. So if you think of examples of gases: hydrogen, nitrogen, oxygen, carbon dioxide, nitrogen dioxide, and the list goes on. If they're under the same conditions of temperature and pressure and the volume is the same, so 100 cm cubes, 10 cm cubes, 5 cm cubes, if the volumes are the same and the temperature and pressure is the same, then the number of molecules of this gas are the same. That's what he's saying. So, for example, when we look at molecules, ladies, remember now, when we look at the molecule of a substance, we're talking about 6 times 10 to the 23rd particles. All right, particles in chemistry looks at atoms, molecules, ions, etc. So we're looking at molecules now because we're talking about gases. So the 6 times 10 to the 23rd particles, right, will be in this example. If we had 100 cm cube of oxygen gas and the temperature was 25 degrees Celsius and the pressure was 101.3 kilopascals, they will have the same amount of particles. So the oxygen will have the same amount of particles if we had 100 cm cube of nitrogen at the same temperature and pressure. So if the volume and the conditions are the same, then they occupy 6 times 10. There are 6 times 10 to the 23rd molecules of that gas. All right. And so they used that concept and came up with what was known as molar volume. Now, what's the molar volume? The molar volume is simple. It is a volume of 1 mole of gas. That's it, you know. The molar volume is the volume of 1 mole of gas. Now, 1 mole of gas, any gas at all, will contain 6 times 10 to the 23rd molecules. So molar volume, 1 mole of any gas, and it will have exactly 6 times 10 to the 23rd molecules of that gas. Now, bear in mind, ladies, we are talking about molecules. So we talk about molecules in chemistry. We know we have atoms. Let's look at nitrogen. For nitrogen, this is my nitrogen atom. And so I write it as N only. But when I speak about my nitrogen molecule or nitrogen gas, the formula changes. It becomes a diatomic molecule. And so I'm going to have to write N2. So when we are talking about the molecules of the gas, ladies, we're not just talking about the individual atoms anymore. We have to reflect on how it is bonded. Whether it's N2, O2, and you know we have a number of diatomic molecules. All right? Just to point that out to you. When we're talking about gases, especially the diatomic molecule, remember to consider that they come in pairs. All right. Now, what are these conditions that Mr. Abagaja was talking about? What were these conditions? So this is where you're going to lean on your physics part of your brain, ladies. So the conditions that he was talking about, 1, standard temperature and pressure. All right. For short, we call it STP. Now, the other is room temperature and pressure. For short, we call it RTP. Now, with these conditions, they are very specific, and they're specific when it comes on to the temperature and the pressure that the particle will experience. So for standard temperature and pressure, or STP, the molecule will experience a temperature of 0 degrees Celsius or 273 Kelvin and a pressure of 101.3 kilopascals or 1 atmosphere. With room temperature and pressure, the temperature is 25 degrees Celsius or 298 Kelvin, and the pressure is the same as being 1 atmosphere or 101.3 kilopascals. Now, this is what they're saying. If the condition is standard temperature and pressure, STP, then 1 mole of any gas, 1 mole of any gas will occupy a volume of 22.4 dm cube. Can be expressed in cm cube, but we mainly work with it in dm cube, ladies. All right. If the gas experiences room temperature and pressure, RTP, then the volume that 1 mole of any example of gas that you can think about, they're going to occupy 24 dm cube. All right. So 1 mole of any gas at STP occupies a volume of 22.4 dm cube. So 6 times 10 to the 23rd particles of a gas, if I put it under the conditions of 0 degrees Celsius and 1 atmosphere, I should get an exact volume of 22.4 dm cube. If I have 6 times 10 to the 23rd particles of another gas, and I put it under the condition of 0 degrees again and 1 atmosphere, it is going to occupy the same 22.4 dm cube. Likewise for the room temperature and pressure. All right. Now, when do we use these? We're going to use molar volume when we are forming the relationship between number of moles, right, and your volume of your gas. So your molar volume provides you with a relationship between number of moles and your volume of gas. But guess what? It's not just going to be that. We can kick it up a notch. And we're going to do that after we look at the first example. So let's look at example 1. It says calculate the volume occupied by 0.25 moles nitrogen gas. Notice the formula there is N2 at STP. Calculate the volume. So we need to highlight some things now. We're calculate the volume occupied by 0.25 moles of nitrogen at STP. So they're very specific when they come on to the question, ladies. They have to tell you the condition under which the gas, right, is experiencing. They have to tell you whether it's STP. They have to tell you if it's RTP. Another thing that you will see on your paper is that just like how they list the RAMs for you, they will tell you what to use, what value your RTP is and what value your STP is. So they'll actually give you whether it's 24 dm cube or 22.4 dm cube. Calculate the volume occupied by 0.25 moles of nitrogen. The answer is here, but let's look at it a different way. All right. Remember now, when we are working from to solve or unknown, always start by writing what you know. All right. And what you know is 1 mole of anything. That's what you know, You know 1 mole, how many particles are in a mole. You know what a mass of a substance would be if you only have 1 mole. You now know what volume a gas will occupy if it were 1 mole. So we start by stating that, ladies. I know that 1 mole of any gas at all, any gas, occupies a volume of 22.4 dm cube at STP. This is what I know. Now, my question is specific because they want us to look at nitrogen. So I'm going to insert nitrogen here. So I now can say 1 mole of nitrogen gas occupies a volume of 22.4 dm cube. But look at my question. They're asking me what would 0.5 moles occupy? That's what they're asking, What will 0.25 moles occupy? All right. What are some ways that you can look at this question? How would you reach at your answer? And do what math suggests, which is to cross multiply. All right. Look again. I want you to bring your attention here. What's the relationship between these two? Look at the numbers. What's the relationship between 1 and 0.25? I have a quarter of something, ladies. I'm going to now divide this by 4. All right. So that's someone with very practical eyes. They will see that I only have a quarter of it. And so I just need to divide this number by 4. If you want, you can do the math way, but you need to look at the relationship between your numbers as well, ladies. All right. It can't just be that you have to follow step 1, step 2, step 3 to realize what you're doing. Look at the numbers, the relationships that are formed. 0.25 is a quarter of my 1, which is my whole. And so if 22.4, sorry, if 22.4 represents my whole, and now I need to split it up into quarters, I'm going to divide my whole into 4. And so my thing will be 22.4 times 0.25. 22.4 divided by 4. It's the same thing. All right. And then that answer will work out to be 5.6 dm cube.